Okay, we talk about the characteristic of a diode that you see in textbook and you see in data sheet. Okay, so what are the differences? And then these are the physical look, okay, of a diode. And then we talk about, they are basically three basic type of diode that you will encounter in power electronics. And then we move on, okay, where I teach you all how to look for the data sheet. What are the important thing? Okay, like for example, the forward characteristic, the graph. Okay, why it looks so different from textbooks. And then I also explain, okay, how do we actually produce that graph. Now in the industry, they have a dedicated machine, okay, that will do the job of this. Okay, in fact, it's very simple, it can actually build by your own. Okay, what you need is a programmable power supply, right? You can turn how many watt, 0.1, 0.2, 0.3. And then you need to have an ammeter and a voltmeter. And every time you increase, right, 0.1 volt, you just write down the current on a piece of paper, then you plot it. Of course, in the industry, they don't do it manually. So they just use, Arduino or some form of microcontroller to do that. So that is the basic principle, okay, to test a real diode. Now, unless you are working in the semiconductor factory, okay, then you may need to know more detail about this. But you are going to like design power converter. This software is actually more than enough, okay, for you to model any real diode that require in your design. Okay. And then I also explain, okay, there are actually many types of modeling method. Okay, so each of them have advantage and disadvantage. All right. Because if you model a very high detail of diode, right, what happens is that when you run your model, it will take longer time to run because you need to calculate more points. So it's about speed and complexity. Unless you have like i7 and above, okay, then you can write, okay, my computer here is only i3. If my computer can run, I believe most of you can, right? And my computer is 8 years old. So very much older than every one of your computer here. So don't tell me your computer do not have enough power to run. Okay, so I explained two different ways of modeling. All right, so I show in linear graph and a semi-log graph. Okay, and I show a tabulated method where you can actually produce, okay, the forward characteristic that is exactly matching what the data sheet is showing. So that means this diode, okay, will behave like how the real diode behave. Okay. So, okay, there are some important parameters like the junction capacitance, where to find this value in data sheet and where to key in. All right. Now we move after that, right? Now we move on. Okay. Now serial connection of diode. In electronic industry, we almost not doing that. Okay, but in power industry, you will see this a lot. Okay, why we need to serial this diode? Now this is because we want to increase the voltage, okay, the breakdown voltage. That means the how many watt, okay, it can handle. Like for example, if you are using this diode based on the data sheet, right? You can go up to, if I'm not mistaken, 1000 watt. It's good enough for LV. Okay, LV means low voltage. Under electrical engineering, LV means low voltage. Low voltage means any voltage that is lower than 1000 watt. This diode satu can handle everything that is under LV. But if you move on to MV, okay, like Malaysia, MV, the next step up is 11 kV. Okay, that will be a problem, right? So if you want to do a rectifier, then you need to serial this one. At least 11 diode, right? Because one is 1000. Of course, you don't serial exactly. Now, if you serial, let's say 2 diode means it can withstand 2000. You serial 3, it can withstand 3. This is how things work. Okay, you cannot find just like one diode can withstand like 11 kV. Okay, so you need to connect them. But bear in mind, when you do that, its forward voltage also increase. Remember, your forward voltage now in this case in power electronic is 1.2 watt. It's not 0.7 anymore. 0.7 is for electronics. So again, if you connect two together, right, your forward voltage will increase to 2.4. Okay, so this is how the power electronic industrial is doing. Now, where you can find this application? Okay, you can find in HVDC. Okay, HVDC means that high voltage DC transmission line. Now, you may wonder, high voltage or all tower one, right? Or AC, why suddenly got DC? Okay, this type of transmission system are usually used for countries' borders. For example, Malaysia to Thailand. Okay, we use DC, HVDC. Now, the reason for doing that is that we can control how much power we want to send to Thailand or how much power we need to buy from Thailand to Indonesia, Singapore. Okay, now to do that, the typical AC electrical stuff will not happen. So it's done by what we call this power, by means of power electronics. So how it works is that, okay, maybe I can show one of the, wait. I have a slide that talk about this. Okay. Okay, of course, I'm not going to go through everything just to show you that in Malaysia, right, we have this HVDC at the border of Kelantan. Okay, so it's owned by TMB. We have this. And then when you look at this, right, this is the principle. Now we got two AC system. AC system 1 is Malaysia, for example. AC system 2 is other country. Okay, now the advantage of using this is that because different country, they have different like frequency, different voltage level, right? You cannot just simply like, take 2 points, connect together, you create explosion. So in order to do this, okay, so they created, okay, like for example, there is a power converter here. It converts AC to DC. Okay, so it's a simple rectifier, but at a very high voltage. We are talking about 132 kV, 1000 watt. It's not like 12 watt, so small. Okay, and then of course through a DC line, because it's already DC, your frequency nuts, right? Your amplitude does not matter anymore. So it comes to the other end. Okay, it's DC convert back to AC to the next, the other country. So the whole substation itself is already made by power electronic converter. So that's why, that's why power electronic is classified as important subject under BEM. You don't tell people that, I'm electrical, I just deal with RLC, other than that, I don't know. Cannot. In the old day, yes. Okay, but nowadays, semiconductor converter is already part of the job scope. So like I showed you last time, you know, in a glance is, you know, just AC to DC, DC to AC. Okay. So of course, this is more complicated than how they connect the transformer. I just skip this, tries to show you. All right. And of course, the rectifier is no longer like what we see in our analog, just 4-diode bridge. We are talking about 3-phase rectifier. So much more complicated. This is how it looks like. You can see this thing is very big. If you zoom in, right, this is the substation, transformer, and you can see this are diode, right? Now, if you are electronic engineer, you will imagine this diode is something you can put on your hand, right? No? But don't be surprised when you walk into a substation, this is how it looks like. And this is the door. You can imagine how huge is that. Okay? And it is water cool. That means it will be very, very, very hot. Okay? So these are the rectifier set. Okay? 2, 4, 6. All right? So 6 sets. Then you may see how come it's so big. When you open up, right, it's just a serial of diode. That connect in serial like what I explained just now. Serial increase the voltage. Parallel increase the current. We are no longer dealing with 1 amp, 2 amp here. We are talking about kilo amp. All right. So same for the other side. All right. Same for the other side. Let me just quickly go through to show you because these are real converter out there in Malaysia. Okay, so these are the cap bank, like I explained, right? Capacitor bank. Okay, these are all in the. Okay, when you go to a substation where you can see something like that out there, this whole area we call it switch yard, where they place a lot of switches. They place a lot of this huge capacitor, huge reactor. Okay, so these are the AC filters and so forth. Okay, these are how the transformer looks like. Okay, in the real HVDC, and this is inside. Okay, like I showed just now. Okay, so these are all the semiconductor water cool. Okay, when you open up one of the stack, this is what you see. You see all the thyristor. Remember, they are no longer like something very small that you can put on your palm. It's just like what I show in my slide, where you start to see all diode, right? Okay, in this type of bricks module, it's no longer something like that you can, drill a hole, put in and solder. It's in the what we call bricks module. Okay, so these are the reactor. It looks like tanky, you don't think that it's water inside, Okay. So I think I will just skip the rest. Okay, these are the monitoring. Okay, so we explain this is how country between country. Now for Malaysia, this HVDC is 300 megawatt. Okay, we're talking mega. It's not like 100 kilowatt, 200 kilowatt. So it's 300 megawatt. Okay, and the DC is 300 kilowatt. And because you see, Malaysia, right, our AC line is 275, 50 hertz. And the Thailand side, right, their AC line is 230 kilowatt. So around 45 kilowatt different, right? You cannot simply like just connect, cannot. Okay, so that is why. Important, when you work as electrical engineer in the future, when you see this type of question, especially border, you have to use this HVDC, and where all the power electronic system will come in to solve this problem. And it actually travel distance of around 110 km. Okay. So you will say that actually 86 km is in Malaysia, 24 km is in Thailand. So usually what the country does is that they just say, okay, you do your part, I do my part, right? And then later they connect. Now they have some agreement on the power exchange. Okay, I sell you how much, you sell me how much, something like that. Okay, this is the plan. I don't know is it happened already or not, from Malacca to Indonesia. Okay, and then they will go through the Strait of Malacca, underwater, come out, underwater, come out again. All right. And then these are the plan for the entire ASEAN country. Okay, where how they plan to interconnect. Okay, what we call this the power, okay, between countries. Okay, I think I will skip this part. This one is just talk about others. All right. And then there is a website. You can actually see this in real time. GSO Malaysia. Okay, GSO is stand for Grid System Operator. Every country have their own grid system operator. So you will see that, okay, right now, okay, currently, right now, okay, 10 minutes before, they update every 10 minutes. So the entire Malaysia, okay, is using 16.8 gigawatt power now. So much power. Okay, so higher record we skip. Okay, it will even tell how much solar we generate, okay, for today. So only contribute to 218 megawatt, so it's so little. Let's see. Yeah, I think last time they allow us to see. Okay, grid code, system data. Okay, Thai line transfer. See got or not? Okay, Thai line transfer, like I said, is a line that connects to other country. So I think today one not update. We try Saturday lah. See got data or not. Okay, line to EGAT. Okay, EGAT is Thailand. Here we call TNB. You go to Thailand, they call EGAT. Okay. So, okay, maybe HVDC. Okay lah, a bit of, negative. Wow, we are taking power leh. Okay, we are taking power. All right. So it actually recorded here. Okay, how much power, all negative lah. All right. We are taking power. Okay, or to EGAT. See, you got EGAT, okay, nothing. No power exchange. But through this one, okay, we have some power exchange. All right. Okay, maybe due to the, you look at it, you can roughly guess lah. Okay, maybe due to the flood happened in Kuantan, that area, right? A lot of place, substation where they are flood, they have to repair transformer, everything. So all the distribution down. So where they get this power from? Borrow, right? Or the nearest you can. Okay, it could be, I just guess, okay, because I'm not working there. Of course, those who working there, they know exactly why they have power taking in, okay, for what reason. So Malaysia consider very good already. We have all this information, right, available for us to know more about, our country, every power plant, capacity. And yeah, the rest lah. Okay. So we come back to the serial and parallel. Now we know that it is important to understand that you connect in serial, okay? Because I believe before I talk about this, your idea about DC is, right, battery 1.5 watt, right? Or your small handphone battery lithium 3.7. Or the most is your car battery 12 watt, that's all, right? For me, it's like last time. My knowledge of DC is, 12 watt maximum. You touch it, you won't die. But of course, now after I get into this electrical industry, I realize shit, DC can be as high as 300,000 watt. Okay. Okay. Now, like I said, same for the parallel. Okay. Now, the diode can carry how many amp? You parallel. Okay. So it will increase. That's why you see just one diode, it's going to be, so huge. Like I see just now, very big, what we call container kind of thing. That have to be water cool. Okay, and they place all the diode there. And where to set this serial and parallel of diode inside a diode model? You can see that here. Okay, remember you have a diode model, you can change exponential, you can change the tabulated, and then there is a number of serial and number of parallel you can set here. Of course, normally, when you are model just one diode, right, you just put 1. Now, let's say you want to model this diode for 11 kV application. Then you need to increase the serial to 11. Just increase that to 11, okay, kV. Okay, now that is so far rectifier diode, okay, general purpose. And I believe this is what we study in our normal analog and normal electronic. That's all, end of story already, diode. Nothing much to learn. But in power electronic, we need to know more, okay? The next one is what we call fast recovery diode. Now you may say, apa ini? Okay. Okay, this is a phenomenon, okay, that will affect your converter at high switching frequency. If you're running at 50 Hertz, you can forget about this, okay? Not a big issue at all, okay? But for power electronic converter, we are dealing with high switching frequency. So if you don't careful about this, okay, you buy a diode that does not support, this fast recovery, you will have problem with the output and efficiency, okay? So that happened in the past when we had 100% physical. Your assignment, I always ask for hardware. Okay, then you will see that everybody use the same circuit. Circuit is the same. Okay, but the output everybody different. Simply because they go different shop lah. Okay, and they don't bother about this. Okay. Okay. Now, what is this? What we call reverse recovery characteristic. Okay, it happens, okay, when you have a diode, when you apply voltage in a forward bias, conduct current, right? Now, when you switch from positive to negative, mean you reverse this one. So it is reverse bias, it blocks. Very simple, right? Okay, you won't notice that during this from forward to reverse bias, right? This diode will actually behave like a conductor. Okay, just like wire, it has current pass through. Now the reason is like, okay, if my two hand, one is P, one is N, forward bias it close, right? So it conduct. So the electron all flow through, conduct. The moment I put reverse bias, right, these two PN junction will become wider. So it turn off, right? Now imagine The moment it open, if we put a slow speed, imagine your hand just like putting a lot of like soap, whatever. It open, there are still electrons, you know, combining with the hole. So that's mean during this a very small fraction of time, in microsecond, it is already reversed, but it still conduct current in both directions. So this phenomenon is called reverse recovery, because in reverse, it slowly recover. All right. Now, you can only see this thing again in the semiconductor factory when they test your diode. The machine is actually doing something like that. Power supply, current, and a switching. And they record it. Then they can see. So now, you can see this phenomenon by doing this. Okay, see, this is forward bias, right? It's on, and the moment you turn off, you see it go all the way to negative, all the way to negative. And then only it slowly go up and then settle at 0. This is the current. So that means this is what we call a reverse recovery. Now, in theory, it should be just off and stop here, right? It won't have this problem, okay? But in practical, okay, you will experience this, what we call reverse recovery effect, okay? Now, to solve this, then you need a diode with a very, very short recovery time. The phenomenon is there. You cannot get away. What you can do is minimize it. Okay? What you can do is minimize it. All right? So you see in this model, right, you can actually model the reverse recovery time in the diode using MATLAB. Okay? You can set the time. Okay, for example, how do you know? Then you can look at the data sheet again. Okay, the reverse recovery time. See, the reverse recovery time, 25 nanosecond. Okay, it's nanosecond. So anything run in megahertz shouldn't be any problem. You put 1 over time, you get the frequency, right? That actually tell you, okay, if you apply frequency higher than this diode will work properly. Okay. Okay, so when you apply that, you will see something like that. You see, it will take some time to slowly go up. And you measure, right? You can even use to measure from the bottom to here. Okay, you can see it's really around 25 nanosecond. You can model it so accurate. Okay, so accurate. Okay. Okay, so now I want you all to draw this from scratch. Okay. I will do one now here, don't worry. I know some of your heart says shit. Oh, don't worry. I will do one round. Okay, open your MATLAB. Those online, okay. Yeah, once you're done, write the screen capture and put it on a chat box. So later I will have a look. Okay. Where is my How Electronic class demo? Devices. Don't worry, I cannot do all the demo I have here. Trust me, the slide, all you have so many demo inside, right? 14 weeks, if I want to do every single one of them, right, I know not time. So I will select a few, I will skip, okay? But this one is important because last week, I asked you to download and run. But this week, I start with very simple for you to construct yourself. So make sure you get the right diode. Remember last week I told you there are so many diodes inside, right? There are diodes that not allow you to model like reverse recovery, all this and so forth. So it is a good time, okay, to actually do some practice here. Okay, while I'm sharing screen, the MATLAB will be much more slower than usual. Okay, those online, okay, yeah, you all can please also start to do this simple exercise. So while waiting, maybe I will try to explain. Okay, what you need is a voltage source, a current sensor, a diode, a resistor, a scope, okay, step function, of course, a ground, and of course, this very important, what we call solver in Simulink. Okay, without this one, right, it cannot work because it's a solver. So it's based on equations to actually calculate that. Oh my goodness, why so slow? Like I said, MATLAB is very memory intensive. Especially I'm sharing my screen now. And yeah, you see it took ages to, maybe I unshare my screen first. Okay, come out already. Oh. Yes, scope. Okay, I will do it here now. Okay, we need to open the library for you all. Just open Simulink, a blank, model. That's why you don't see anything this, right? So now you need to go and find all these parts, okay, to drag into here and start to connect them. That is I3 speed lah, okay? For because these are the all very common component, right? You will use throughout the power electronics. So just make sure that you know where they are, okay, and you know where to locate them. Yeah, next time I should start this before I come to the class, so it's faster. Okay. Now, of course, you got the Simulink here, okay? Now, in the Simulink, right, what you need is the scope and the step function, right? So it is under the sync. This is where you find your scope. Drag over. Under Simulink, sync. Drag over, and then the next one is source. Right, under the source, you will have a step function here. Step. Okay, also drag over here. So you got a scope and you got a step function. Now, after that, you move to Simscape. Simscape. Under Simscape, there are electrical. Okay, so inside electrical, then you can start to look for semiconductor. Yeah. That is where you find your diode. Okay, that is where you find your diode. And then after that, I think the rest, you can go to the foundation library under Simscape also. Foundation library. Inside the foundation library, there are electrical, right? There are 3 blocks here. One is element. This is where you get your resistor. Drag over here. Okay. You get your resistor and you get your sensor. Right? You need a current sensor. So you drag this one. That is where you get your current sensor. Then after that, you go to the source. You need to have a controlled voltage source. Control voltage source. Drag over here. So now you have all this already. Now left only, okay, ground, electrical reference. There will be your ground point. You need to have electrical reference. Then after that, done already, okay, you will go to utilities. Utilities, you will find the solver configuration. Okay, drag down here, solver configuration. And then there are 2 blocks here. This is to convert the line to this, or else this one you cannot connect. Again, the output of this one, right? If you don't use this converter, right, it cannot connect. So what you need is that, you see there are 2 converters here. PS to Simulink. Okay, physical system to Simulink for the scope. And then Simulink to physical system to the voltage source. Okay, so that's all you need. That's all you need here. So once you connected, okay, of course you need to set your resistor, so you determine your current. Okay, so you double click them. Okay, yeah, I put 100 ohm. I put 100 ohm. Okay, this is what you need to set. Okay, the diode you no need to set first. Okay, because for a quick try. And then very important is this one, the step function. You double click the step function. This one I already put inside my slide. You will need to set, okay, the step time. Okay, like this one is 50 nanosecond, E -9 nano. All right. That means at 50 nanosecond, it will become reverse bias. And then initial value is 5 volt positive. Final value is -5. So when you set this, right, you will see this. It starts with positive, and then it go negative. So when this is done, and your stop time, your simulation time, you need to set at 100 nanosecond. Okay, 100 nanosecond. Okay, let's see. Okay. Again, first time it takes some time to run. Then after that, it should run faster lah in the next time.
Hello, sir.
Yes.
So what is the thing beside the step function? The component beside the step function?
The step function. Okay, the step
to,
function is the voltage that's going to apply to this voltage source. Meaning that, you know, it's a 5 watt positive. And then you switch to reverse bias at 50 nanosecond, right? To -5.
Okay, thank you, sir.
Okay, you can see in my slide, I actually put this important information. Okay, in my slide here, you can see here in my slide. Refer to my slide. Okay. So okay, this is how you see the reverse recovery. Right? You look at the scope. Okay. Now you use Ohm's law to calculate, right? 5 watt divided by 100 ohm. Okay, so this will be your current 0.04 something. Remember voltage drop. Okay, and then when it switch, right, you will see this reverse recovery. So once you get this done, then we will move to setting the reverse recovery. Okay, so I walk around in the class. So okay, you all doing? Can get it? Can, right? Yes.
That one, the function, right, there are two arrows, right?
Where got two arrows? Arrow, this one.
Sir,
This
what
arrow,
the voltage source you use already?
This arrow is under this utility. There. This one, you see the car, you see this is Simulink, this is physical system. So is this one, no? Simulink to physical system, this one. If you use the wrong one, right? When you try to connect, right, you won't connect if you use the wrong one. Okay, online one. Wow, online one. Wow, Huan, very fast.
So which voltage source using already? The voltage source name.
Okay, online one, we start to has very good. Okay. Okay, Tang Kai Hong, Ayo Delhi, Joseph. Very good. Okay. Everyone can, those with the computer one I'm talking about. I mean, you don't bring computer, you don't tell me cannot. Okay, cannot in front row. Still doing. Oh, good. That means I can relax. Never mind. Okay, because if you don't get used to all this, right? Later, I tell you, nightmare. Wow, why you look like so? You know, this is so big. But don't worry, you can always improve video. And all the students, still get over. model, this diode will not stimulate the reverse recovery. Yeah. Simulink electrical semiconductor gets it diode. Okay, this is a very common mistake. When students happily show me the result, we work in the converter, but they're using the wrong diode. So when they come to make the hardware, you will always get the different result. Okay? Okay, online I believe should be okay, right? All of you are having computer in front of you. If you all still review to practice, okay. Yes. Yes. This one. Solver configuration. Under Simscape utility. So now you realize it's very important to know where they are, right? Instead of knowing their name. If you type diode, it will show you so many diodes. You don't know which one is which one. Okay, I go to the washroom for a while. Okay. Okay. Khalid, okay. Wong, Ouyang, Rico. Okay, very good. Xiao Chang Hong, okay, good. Okay, I think we need to move on already. I cannot wait for everyone to do. So this will give you some idea, okay, how you model, how you can see this phenomenon. Okay, so now let's say one day you want to design a converter that requires the use of a diode. Then you want to make sure that you model this reverse recovery properly. So what you need to do is that, okay, you need to go and find a data sheet of a diode that claim to have fast recovery. Okay. Now, what we are modeling here, right, is theoretical. That's why you see like, oh, very fast. Okay. Now, everything is the same. You don't need to do any changes. You just need to do some diode, setting changes. Okay. As long as your first one is working, then it shouldn't have any issue. You need to remember this reverse recovery is caused by the junction close together and open, right? So when they close or open, they actually form a capacitance. Okay, so it's under the capacitance cap. So under the capacitance cap, we will see. Wait, I don't forget already. You look here, dynamic. The charge dynamic. Remember, because the moment you open up, there are still charges, Hole and electrons still flowing. Okay, so we want to model that, what we call dynamic. So of course, normal one, we say do not model charge dynamic. Okay, that's why this model, you still see reverse recovery, but very fast. But this type of speed, right, you cannot actually get it from the market. So when you really buy a diode from the market, okay, you need to change this to use peak reverse current and reverse recovery time. Okay, 1, 2, 3, the third one. So once you set this thing, you will have other option. You see, that is where you can key in this 25 nanosecond. Now, like I said, why 25? It depends on the diode lah. Okay, if you are using this diode, then you see, oh, what is the reverse recovery time? So one is set. Just click apply. Click OK. Okay, and then you can run the model again. And now you can see that this is the real reverse recovery. Okay, you can see it's actually quite large. Okay, just now very small. Like I say, it's very theoretical. But this is a real diode, and it will be open up. Okay. Now the next thing, I'm going to teach you how to do measurement here. Okay, on the time. Because it is important for you to do this in your assignment report. You cannot show me this one, sir, 25, you look for yourself lah. I cannot take the ruler and measure, right? So what you need to do is that this scope, right? Let's say you open Max, you click this one, okay? You click full screen, small screen also can. Okay, now you can see that, there are measurement. There are T1 and T2, okay, where you can actually move the time. See, you can move this. You can move, all right? And then it will show the magnitude and time. Okay, it will show the magnitude and time. Okay? And then this is the second line. You see there's a 1 and 2, right? You just move. Okay. Somewhere here lah. Okay. So you can see the difference of the time here. Okay, it should be somewhere around, somewhere it's about to go up. Okay, somewhere around here. Okay, that will be around 25 nanosecond. Okay, so it measures the time between these 2 points. Okay, between these 2 points. So approximate, right? So it will give you, oh, okay, these are the time. You can see when you move this, right? These are the time. These are the magnitude. Okay, the T1 value, you see it's negative. All right, so you can move around. Okay, roughly. Okay, around here. Now after that, right, you will see here 25 nano. It will convert it to frequency for you. 39, okay, roughly around 40 megahertz. That means if you use this diode, right, you can using switching up to 40 megahertz, not more than that. When you switch more than that, right, this diode cannot handle anymore. Okay. So this is how you do the measurement. Of course, you can switch back to the normal one. It will show you something like that, lah. And once you are done, right, you just click this one, it will back to normal. Okay, so this is how you deal with the measurement at the time. Okay, do some measurement, the magnitude at the time difference between 2 points. Oh, super fast, those online one. Okay, Fong Tun Ho, very good. Oh, why you got it wrong? Yeah, if it's wrong, then you try just, follow the step I show in the slide. Of course, so small I cannot see lah, but I see that it does have some reverse recovery. Okay, Ching Eun, this one look nice. Tae Bun Hong, okay, good. Okay, Osama, okay, good. Physical class, okay or not? Once the basic one work, right, the rest should work, Okay, Rico. Okay, good. Yeah, the register value is 100 ohm. In fact, you put 10 ohm or you put 1000 ohm also okay, because it only changes the magnitude of the current. It does not change what we call the reverse recovery time. Okay, Tang Kai Hong. Okay, good. Okay, so I think I need to continue already. So like today, okay, you all already know how to create simple circuit to test a diode recovery from scratch. Okay, so this, if you can get this, that means it's okay already. And you have to understand these are the things that you need, okay, in order to make a complete circuit. Okay, good. All right. So like I said, those with no computer, you can always follow my slide. If and or video, you should be able to reproduce what I show here, okay? Okay. Now the next one is what we call Shockley diode. Very hard to pronounce for me. Okay, it's by the guy called Shockley, the guy, one of the co-inventor of the diode. So now the difference between now we know that diode not just, pass current and block current. It have this what we call reverse recovery characteristic. And also we know that the forward voltage is actually an issue. If it's too high, also no good, right? So Schottky diode have an advantage of the forward diode voltage is very low, lower than germanium. Okay, it's lower than germanium. Like just now we see, the power diode we use is 1.2 watt forward. Okay, now all this voltage drop, right, will cause these power losses, will decrease your efficiency. All right, so they come up with another type of diode, okay, that will actually give you a very much lower forward voltage. And you can buy this type of diode, okay, it's 1N58XX, okay. Okay, so it looks like normal diode. The only difference is, like I said, it has a lower forward voltage. Of course, the rest, this is also the same forward characteristic. Okay, you can model it using the previous model. And then how to model that? Okay, to model, you need to go to the, you see, we have done the main, we have done breakdown, we done the capacitance, right? Now the next one is under temperature dependence. Okay, so under temperature dependent, you can actually set the energy gap, okay, to Schottky barrier diode. So by doing that, okay, you can actually model, okay, the Schottky diode. All right. So it is here if you want to look at the real diode. Okay, the first one again, in summary, you can do your serial parallel here. You can do exponential or, tabulate. Breakdown voltage, okay, I said infinity. By right, it should be 1000 watt. Okay, that is the breakdown voltage. Remember this one, because normally, okay, I will just put infinity because I don't bother. But in real practical, you don't do that because it will run. You will say, oh, design cantik, and then you go in principle, then they turn on the moment bomb everything because you set this infinity. Okay? And then we have done this capacitance junction that will cause the reverse recovery. And the next one, okay, will be the one that allows you to model the, okay, now this one, normally we model the silicon, right? Then you can select Schottky barrier. Okay, so you can select this one. All right. And then of course, you don't forget to also, make this correct because you see, this one is still like 0.6, 0.7. You have to model everything, all right? Okay, so this one, okay, I don't have any simulation for you. Okay, so for now, we have gone through all three different diodes already. Now the next one. Okay, this is application of a diode called freewheeling diode or flyback diode. Okay, this is application of the diode. Okay, so why we need this. Okay. Now this application means that you will see that, okay, we have an inductor load. All right. And then we have a diode. Okay, that is connect, okay, parallel to the inductor load in a reverse bias. This is your source 12 watt. Okay. Now we again have a step function here. So it's a switch. It's a switch that I turn on in. Okay. This one you can see I also have another switch here. Okay. So this switch, when I put 0 means turn off. I put 1 means turn on. All right. And then we have to measure the voltage across the inductor. Okay, the voltage across the inductor. All right. So what happened is that the moment I turn on the switch, current will flow through, right? Will flow through. And then it starts to charge the inductor, positive, negative. All right, charge the inductor, okay, in the form, I store the energy in the form of magnetic, okay? Then when I turn off, the moment I turn off, right, if there is no freewheeling, means that this one is off, okay, you will see the plus and minus, right? When the inductor releases energy, the polarity change, all right? And the polarity change. So what happened is that the voltage will be very, very high, okay, because of this inductor. Okay, the voltage is high because it's this voltage plus this voltage. It becomes serial, just now parallel. See, just now parallel, it becomes serial. So this will actually cause, okay, damage to your MOSFET that is in the circuit. Of course, this one we are MOSFET just to show the idea of using this diode. Okay, now what happens if you have a free-wheeling diode? You see, the moment it changes, right? Charge plus minus. So this diode is reverse bias. So when I discharge, you see, plus to the anode, minus to the cathode, right? So it starts discharging, neutralizing the extra surge energy that's stored in the inductor, so that it won't release in the circuit to damage, okay, the transistor. So that is the idea of the free-wheeling diode, has to be parallel to an inductive load. Okay, now if we do this simulation, so what we will see is that, okay, now without free-wheeling diode, you see when you on and off, right, you will see a very sharp spike happening. And the spike is not like 1 watt, 2 watt, 10 watt. If you look at the unit here, it's thousands of watt. Okay. Now, if you have a free-wheeling diode, the spike is gone. You see, this is 12 watt, right? You turn off, you go to 0 watt. Okay. It's not 0 It's below 0, negative 0.7, which is the reverse, the blocking voltage of this diode. Okay. So this is the phenomenon where you will see, this inductor, right? It's actually in real application, they are motor. Okay, they are motor. All right. So every time if you try to control motor, you need to have a diode parallel with, or else it will damage your, the chip itself. Now, especially for mechatronics student, you're dealing a lot with motor, right? Small little motor control thing. One of the example of this, wait, I think I should have the data sheet. Oh. This one. Okay, L293. L293 is one of the very common L293 motor drive. Okay, this is a chip commonly used in Arduino. Okay, when you buy those, you can see it comes with all this what we call motor drive. Okay, see, these are the standard chip L293D. You can drive 4 motor using this chip. Okay, now the thing is that when you look at the data sheet, okay, let me find the data sheet. Oh. Okay, now you look at the application note on the data sheet, right? You will notice that it even tell you when you want to control this motor, right? It will draw a diode here, right? You see the diode is reverse bias. So it tells you that make sure you put this diode is a freewheeling diode. Every time your motor rotate in one direction, reverse direction, it will create, okay, this what we call spike voltage. Okay, because of release of this motor inductive energy. So this diode there is to neutralize it. Okay, so you can see that it tell you, hey, don't forget to put in the application note inside the data sheet. It show you must put. A lot of students when they look at this usually they go Jalan Pasar to get a chip, happily come back, you see as I put a breadboard, and you see got diode, you say don't care, right? You just plug until it run. Then you say, bullshit lah, you see, can run. Of course, this thing won't damage your board on the spot. That is what happened lah. Can run, right? Tomorrow go demo in front of lecturer, cannot run already. Then I say, sir, yesterday running. Then I look at it, I believe you, but I still minus your mark because you don't put diode. Okay, now another thing. Okay, now it will show you, see, how important to put this diode for this application. Because power electronics, right? You're dealing with a lot of control with motor. Now another tricks here. Okay. Now you look at the same chip, L293 with a D. Just now I show is L293, no D. What's the difference? The difference is that with the D, inside the chip, they already have the fly back diode for you. So this answer another very strange phenomenon student have. You go to the shop, you buy same chip. Why my one always spoil, your one never spoil? Both also don't put diode. Because you are so lucky you get D. Hey, it's true. You go Jalan Pasar, say, hey, I want motor driver L293. The guy will go to the tray, open up and use a hand piak. Nah. please look carefully before you pay, because they mix with D and non-D. And they have been selling this component for decades, Jalan Pasar. They understand all the students already, because they know the moment after demo, they don't go bother the chip anymore, right? So yeah, this is how the thing works. So when I do demo testing or whatever, I always look at this, I will start to laugh. Especially those yesterday working. The most important one, this morning working, why? I look at it, no diode, no D, sure die lah. So sometimes they cannot understand why their friend one can survive, because they are so lucky. They get the one with D, okay, without diode. So don't underestimate this very small diode thing. Like in this mechatronic, robotic project, it causes a big difference. It does, remember, it does not damage your motor or whatever immediately. Because it's, like I say, it's a small spike. Every time 1,000 watt, maybe 10 times gone already lah, right? The time you show me is the number 10 times, no? So things never work out, all right? Okay, I think it's time already, so I'm not going to do MATLAB demo on this. If you want, maybe I can show in the next class, lor. Okay, because these are not so important in the sense that for your power electronic converter, but you need to know they are something like that will happen. Okay. So, okay, 6:30 already. Wow, bad network. Okay, any questions? Okay, if no question, then we will end the class today. Okay, thank you.